Okay, my wonderful, outstanding friends, as always, I am the problem. I'm going to start trouble. Yeah, absolutely, because carbon dating is a problem, a very serious problem, and I'm going to show you why, and it is a terribly serious problem. Look, in the vast majority of nucleophilic substitution, that means you replace something with something else. These reactions you will see in this and other organic chemistry, which is human and other biological chemistry. Electrophilic atom is a carbon which is bonded to an electronegative atom, usually oxygen, nitrogen, sulfur, which is a nucleophile. Now, this is nucleophilic substitution. Well, what is nucleophilic substitution? Well, here's what's going on with nucleophilic substitution. They're leaving groups. They're nucleophiles. They come and they go. Nucleophilic substitution is where you bring in new molecules and take some other molecules out, and they're primarily carbon-based interactions. Now, well, what is carbon dating? What they say, this is what happens. Carbon-14 is a weakly radioactive isotope of carbon known as radioactive carbon. C14 dating is only applicable to organic, which is life, and some inorganic materials, but not applicable to metals. This is nothing to worry about. What is radioactive dating? All right. Radioactive dating is a method that provides objective age estimates for carbon-based materials originated from living organisms. But the problem is they think that the carbon fixes when you die. It's no longer moving through your body like it normally did. Well, yes, it does. It moves all over the place. And here's what they're saying. The impact of the radiocarbon dating technique on modern man has made it one of the most significant discoveries of the 20th century. It's completely wrong. And I'll show you how wrong it is. No other scientific method has managed to revolutionize man's understanding not only of his present, but also events already happened thousands of years ago. Archaeology and other human species use radioactive dating to prove or disprove theories. Well, I'm going to tell you what. You're starting from the wrong premise again. Every single time I see this in science now. And then they say follow the science. But let me show you where the science leads. All right, so here we go again. How does carbon dating work? Well, here's how it works. This is the assumption they make. This is the basic principles of carbon dating. It's got to do with carbon-14 and carbon-12 and the different isotopes, and they have guesstimated that a certain number of decays will happen in a certain number of years. Therefore, listen to this now. This is the key. It's unbelievable that they think this. Plants and animals assimilate carbon-14. That means they take it into their bodies from carbon dioxide throughout their lifetime. So they accumulate it. When they die, they stop exchanging carbon with the biosphere, and their carbon-14 content starts to decrease at a rate determined by the law of radioactive decay. So they're saying it was exchanging. So you had carbon coming in, carbon going out, carbon coming in, carbon going out, and all of a sudden you died, and that all stopped. No, it didn't. Absolutely did not. It continues on, and that's what causes all of these mud fossils. It's just totally wrong. It's not right at all. Now, like I said, the carbon are the nucleophiles, and what's a leaving group? A nucleophile acting in reverse. Well, they're leaving, the carbon is leaving, and something else is coming in. What makes a good leaving group? Now, something I find very interesting. I've been screaming about nucleophilic substitution, creating the mud fossils for a couple of years now. Creating the bones like this, turning into mud, I call them mud fossils because they take on whatever the chemistry is around it, and they give up molecules and they take them in, and eventually they turn into stone when they dry out later. But in the meantime, there's a continuous cycle of nucleophilic substitution going on in here, which is the leaving groups. Some come in, some leave. That's how they stabilize. So for them to think that the carbon fixes, and that's what they say. Well, the carbon fixes when you die. It doesn't move anymore because you're dead. No, well, that has nothing to do with it. If you're in any kind of moisture or any kind of atmosphere at all, especially in mud and moist conditions, it's continuously movement of molecules in and out until it forms stability because of the nucleophilic substitution. They're substituting molecules. It's as simple as that. All right, this goes back to 1950 or somewhere around there. It's about carbon-14 kinetic isotope effects in nucleophilic substitution reactions. That's exactly what I've been talking about. Well, what are kinetic isotope effects? Well, these happen on these, well, you're never going to understand it. But this says the surprisingly large kinetic isotope effects in these S sub N2 reactions. Well, what is S sub N2 reaction? Well, here's what it is. All right, here they are. Isotope, remember I said a kinetic isotope effect? And this is where you have these S levels. In physical chemistry, a kinetic isotope effect, KIE, is the change in the reaction rate of a chemical reaction where one of the atoms in the reactant is replaced by one of its isotopes. That's what they're looking for, different isotopes in atoms. This is all nucleophilic substitution as it starts to find its way into stability. This is not from, I guess it is a breakdown, but it's not something that fixes. It's always moving through the chemistry. And it is a rate of breakdown. I have to agree with that, now that I think of it a little deeper, because it's looking for stability. So anything that's not stable is going to drift towards stability at a fairly consistent rate. I agree with that. But to take all of those molecules in that creature and say, okay, they're all moving at the same rate and they're all stuck here and nobody's moving in and out, that's not true. Well, right here, this is nucleophilic substitution of carbon-14. But this is exactly what we're talking about, kinetic isotope effects. And this goes back to 1957. So they see all these things and they forget them. I go back to the earliest, of course I'm a million years old, but I wasn't looking at this stuff back then, but you can find these things when you start searching for really things that make sense. You have to look up, I forget how I got to this, to find this, but I put something in, looking for nucleophilic substitution in carbon-14, something like that. And you keep digging and digging and digging, and you'll find all kinds of different stuff. Sometimes it'll conflict. And then you say, who's right and who's wrong? Because basically everything I look at is conflicting with the current theory. Absolutely conflicting 100%, everything. And it's because of electron flood theory, first of all. It's because of assumptions these people make, like the carbon fixes when you die, totally wrong. Light can't slow down, totally wrong. Light can't accelerate, totally wrong. Then they don't think you can't see these light particles with cell phones, but yes you can, because you can see cosmic rays with cell phones. They made a big thing out of it 7 years ago. And the particles of light we're looking at are so highly accelerated and energized that they are exactly identical to cosmic rays. And we're right on top of them looking at them. These cell phones can look into space and see them. So there's a lot of thinking to do here that is not being thought of, and it's leading to just a disaster in science because everything is denied instead of looked into. That's what's happening right now. And I'm telling you right now, it's been 10 years, and the only reason I stepped into so many other fields of science is to expose them for what they're doing here. It's nothing more than pay us, we'll tell you what you have to say, and if you don't say what we tell you, we'll fail you and ruin your life. And you're not going to get a good job unless we give you a piece of paper that says you're willing, you can repeat what we told you. And nobody else can come in and make changes because we have a bunch of guys that are called peer reviewers that will stop them from talking, that nobody will listen to. So you better pay us, you better be quiet, you better do what you're told, and we'll give you a piece of paper. All right, from what I can see, they knew more about nucleophilic reactions back in 1957 than they do now. I think they're just starting to get into this again because I've been screaming about nucleophiles and why not they're paying attention to this. Because this is just updated March 27, 2021. I find that everything I'm screaming about all of a sudden becomes a hot topic. Now, nobody will respond to me, but I think they're responding to what I'm saying because nobody can deny it. The things I'm showing are just undeniable. And these are leaving groups, are nucleophiles acting in reverse. I've been talking about nucleophilic substitution for years now, because that's the only reason the mud fossils turn stable. So now they're talking about acting in reverse, because if you put something in, obviously something's got to come out. So it's a leaving group and an invading group. That's all it is. And so carbon does not stay there and fix. Nothing ever leaves. That's just not correct. I don't want to be rude, but it's just not right. All right, so don't forget now, in the vast majority of nucleophilic substitutions you see in this and other organic chemistry, the electrophilic atom is a carbon which is bonded to an electronegative atom. That means it's moving around. So the carbon is coming and going. I don't see how you can miss this. But the problem is that the people that should be listening only want to dictate. They don't want to listen. And somehow we have to get a forum outside of the mainstream so we can discuss these things without the people being fired from their jobs. They can call in, and pretend they're somebody else. And we could talk about these things and get it out in the open. Somehow it's got to be done. I can't really do it. I need somebody to organize it and get people to, get some kind of a format going where we can have, interactions, questions and answers, present evidence like I always do. But I need a bigger audience. I need a bunch of people. I need people that are in other areas other than alternative, because I got a lot of people that nobody's ever going to listen to because they, a lot of stuff they're talking about just is kind of crazy stuff too. I attract those kind of people because they're open-minded people, to be perfectly honest with you. They're smarter than the academics. Academics are totally closed-minded and absolutely refuse anything that upsets their authority. That's the key. Very, very distressing that they're the ones that are in control. And I mean in control. You cannot stand up against them. All right, if the things I'm saying are true, what impact do they have? Well, what is everything based on right now? Our history and all kinds of things. Well, how does carbon dating work? I think I showed it does not work, and because it's being continuously replaced. So what is the effect that would have if things I'm saying are true? What is radiocarbon dating? Radiocarbon dating is a method that provides objective age estimates for carbon-based materials that originated from living organisms. We went through this before. And an age could be estimated by measuring the amount of carbon-14 present in the sample and comparing this against an internationally used reference standard. Now, I disagree with all these things, to be perfectly honest with you, because they don't understand the nucleophilic substitution, which I just showed you happens. Now, here's what the impact is. It says the impact of radiocarbon dating techniques on modern man has made it one of the most significant discoveries of the 20th century. No other scientific method has managed to revolutionize man's understanding, not only of his present, but also of events that already happened thousands of years ago. They're basing everything on this assumption that carbon fixes, and it does not. Archaeology and other human sciences use radiocarbon dating to prove or disprove theories. And I can tell you how they do this. It's very simple. You can find all kinds of different dates on the same item. You just have to look. This has to be examined other than just accepted, because it's not true. What they're saying is not true. And I think I've shown that it's more than likely not correct. If they're dating things based on the fact that carbon fixes and does not leave, nothing else comes in, that is just wrong. Okay, that's the end of my story for today. I love you all. Somebody's got to start stepping up and confronting, and we need an open forum. I will debate anybody, anytime, on any subject that I present. I present evidence. I want somebody to come back at me with some other evidence that can overwhelm my evidence. Now, I know people can come back with evidence. Oh, we saw this happen, we saw that happen. Well, let's see if it overrides my evidence that says I can account for that, I can account for this, and my shows that that's insignificant or it's wrong, one or the other. I have to be able to do that, and I can, and I'm not being allowed to do it. That's the key. That's what upsets me. I've been screaming about photon collisions, and we can force them. I've shown that a bazillion times, creating dark matter, muons, bosons, the whole 9 yards, electron showers, and here they are talking about it now. Colliding photons were spotted making matter. Colliding photons, making matter. No, they're not. They're separating matter. They're taking the dark and separating it from the white, shown it a million times. And this is Brookhaven National Laboratory, detects particles producing da da da. And I'm having a kind of a real go-around with Fermilab now, Don Lincoln, he refuses to look at the stuff we did. And we created exactly what they're asking for. Well, I'll show you that right now, too. This is precisely what they're trying to get to, the smallest particles that exist. This is what this whole thing is about. What is everything can be reduced to? Well, they have seen these muon neutrinos attached to these electron neutrinos, a white ball and a black ball. And they've seen the muons, when they concuss, they do not do anything. They just stay the same. The electron white ball part explodes and turns into showers. And this is precisely what we show right here. This is the concussion event where the black and white balls were attached together. They separate right there. That is fission. This is exactly the high energy particles, the white electron showers I just showed you. And then the black balls, which are the muons, come back together. So before they collided and exploded, they were the neutrinos. When they explode, the muon doesn't change. It still stays a muon. The white turns into white electron showers. Precisely what we see right here. There's the muon, does not change, stays the black ball. There's the electron neutrino, explodes into the white showers. Very, very hard to deny this. Now that's from research done 6 years ago. I presented this to the University of Geneva and everybody, all of the big shots, and not a single bit of interest. And that is light accelerating. The particle was here. The particle exploded here. I just showed you it's separated from the black and the white. And the black and the white, I will show you how that manifested itself. All right, here's the light coming in from here. These are laying down particles right now. As they start to concuss at the venturi, they tip sideways. They call this neutrino oscillation, flat, then sideways, and then the box, and then the explosion. That is coming in, and otherwise you never see them. You see up here, you don't see any particles there. Well, they're there, but they're starting to concuss way down here. Here they're very, very energetic, because that's exactly in straight in line with the venturi. Like this one concusses way back here. Normally you would have the cookie-looking ones, the Oreo cookie-looking ones, and then they twist up here like they do here, and then they get really glowy just at the venturi. But we just happened to catch them right in the middle and boxed where they were. You can see there are two particles attached together, and they're 2-bar magnets, one here and one there. And that's what a photon is. This is light, so this is not huge particles like Fermilab and the rest of them. I don't know about Fermilab. I'm not going to talk for them, and they won't talk to me. So, but I know that the Large Hadron Collider was hundreds of billions of particles together, and then digging it through the debris and seeing these little things here and there, but having no clue where they came from and what their purpose in life is. They are light, they can divide, they are particles, they have mass, they can do fission at the Venturi, and when they come back together, that's fusion. Look up nuclear reactors, how a fission reactor works. Only it works on a macro scale, big gigantic particles. We're using light, so we're never going to run away, but we're doing basically the same thing. All right, don't forget, here's the recap. Red pulse laser, that's all it is, red pulse laser, it's photons. And a pulse, 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 the particle is out here. We saw the particle before. And this is the acceleration. And if you can't see acceleration, I don't know what to say. And if you can't see the increase in energetic value, you see that explosion? There's particles coming through the air up here just like there is right here. But you're never going to see them because they're not concussed enough. This one's going straight into the Venturi, so it manifests itself way out here. These would not manifest themselves. You would not see them. The only reason we're seeing these ones right here is because of this energetic explosion. That is just absolute devastating energy power here. Just exactly like an atomic bomb going off. Literally, I'm telling you, that's what I'm seeing. If you're seeing something different, I'd like to know why. But you can see these are waves just like this was. But you don't see them. They're over here. They're coming forward. The rest of the wave is still here, just like this one still has this wave. Well, the only way you can see it is to have it concuss so violently that it glows. And that's what's happened with the one that's directly in line. That's why I showed you one particle turned into the box right at where it should, and one's turned in back here where it shouldn't. Well, it should, because it's in exact direct line with the Venturi. And so it's the most concussed. And therefore it's showing its true colors right at the Venturi, but a little bit further out. So it was probably out here somewhere. But they come back together instantaneously. This is light speed, so this is like instant, done, case closed. And in the midst, I think there's a hell of a lot of energy right here. As you can see, if you could some kind of ball it up into something and shoot it down into, because this is electrical energy. This is electric power. All right? Light is nothing more than electrons back to back, as I showed you. And these are electrons, and they're back to back. One here and one there, one here and one there. And when they smack and concuss, they have mass. And mass is dictated by more than just the weight of this particular particle. The weight of that particle is only part of the equation. What did it hit? Did it hit something solid? Did it hit something mushy? That will depend on the dissipation of the mass. You know, you're always going to have the same weight. Even the green ones, they're identical particles, absolutely identical. So you're going to have an identical weight, but the green impact much harder. All right, one last thing, and this is very interesting to me. I showed you these things spinning like crazy, and because the green light is smashing the red light down, which lifts the green light up, which is shooting straight up in the air here. You see it? That normally would just come straight out of here, but it's being forced up, and I think we can force airplanes up by putting lasers under their wings and creating turbulence under the wing, which makes the wing sort of float on something more substantial and would create this lift just like that. It would be fun to see somebody in an airplane club or something, little airplanes, little model airplanes, try something like that. But you can see it's creating a pad for this to sit on, and that light is pushing up just the same way an airplane would. It's pushing away because of the laser has excited that light to form like a bubbles of like a foam for it to ride on. Basically, that's what you're looking at. All right, I told you the green is identical to the red, and there it is. It's identical. Now, this one's just getting in there, just about to explode into bits and pieces. Remember they came in like sideways like this? Originally they were flat, then they turned sideways, then they exploded. Well, that's what's going on here. Now, is the green more powerful than the red? Hell yeah. Hold on, here it is. They're coming through the Venturi at the same time this time. You see what happened? This is the red laser if it was all by itself going through here, you'd see a nice red laser coming through. Well, the green is above it on the same Venturi. Well, it's so energetic that its particles, I just say, get the hell out of my way, and the red just pushes down out of the way. There's no red laser coming down here. That's the red laser. It's almost 99% of its particles are just forced down. Look at how they spin. You see these little circles? I don't know if you can see that. Let me come up close. This is very, very cool. You see those little circles? All right, they do not make those circles normally. Those circles are made because this light is sort of coming through sort of lazy, and that's saying get out of the way. And when it does, it spins it like crazy, and that's what making these little circles. This stuff is fascinating if you take the time to look. And then up there you can see. Whoops, maybe you can't see that. Up there, there's a little tiny bit of red has come through, and just so you can see that these greens are the same particles, you know, he's showing them the box configuration basically as best he can get it. But we have a lot of really fabulous shots. Let me show you something real quick, and then I'm going to leave it at this. I didn't mean to go down this road, but if you don't understand everything about physics and chemistry and the atoms and all that stuff, you're not going to understand nucleophilic substitution. It's electrons attaching to other electrons and giving up other electrons, and they sit in the middle of the periodic table, and that's why they can give and take electrons, and they have deep orbital holes. So there's a little work to do other than to just scoff it and walk away. These are the Higgs fields, and these are the particles spinning. And these again are this is really looking right into the Higgs field coming at us. And the darker the spots are, the harder they're impacting. And down in here, they're being crushed. So it's really how hard something's being crushed is when it turns dark. They're in the pockets in between, so the fields on those are squishing it. That's why you can see a little bit of darkness here in the middle of where you wouldn't expect it. They'd be normally kind of yellowy looking. Only the tip, because that's the tip, and it's like sticking out. Just like this. You see these? These are sticking out. And that's basically what this is. It's virtually, it is what this is. I'm sorry. It is what it is. And the center is furthest out. So that's a cone going back. And they have troughs. And that's a trough, and it's crushing as a trough. That's why that's pinched. That's not accelerated light out. That's pinched light. And the same thing is going on up there in these troughs. And these are the Higgs fields, and you know, I mean, it's a very, very interesting research that needs to be looked into deeper. That's my recommendation, and you know, I think we can get free energy out of this. But it's you cannot get anybody to pay attention because they won't peer review you. So it becomes unknown and is not allowed, basically, is what it boils down to. Because I'm trying to get Don Lincoln to debate me about this, about the muons and the electron showers and all the things they're asking for. I said, these are all the things. He said, oh, no, you have to leave it to the pros. I said, leave it to the pros. You guys get deniers. And that's when I started putting out some kind of, it wasn't very nice. Well, it was true. The stuff I told him, I said, Don, I'm going to put some nasty stuff, not nasty, but well, maybe I did say nasty, but I said it's not going to look good. It's going to be, you know, unless you want to debate, I'm just going to keep whacking you. That's all I can do. You make statements, they're wrong, and if you won't respond to my statements, then I'm just going to say you're wrong and just deny her. And that's what's going on right now. And that's not just him; it's everywhere. I kind of like the guy. I really do, to be honest with you. I was really hoping we could get along, but I don't think that's going to ever happen. But who knows? Anyway. I'm perfectly willing, Don, my friend. All right? I got a lot of things I'd love to talk to you about. If you're a scientific guy, and you seem to be very responsive. He was very, very cordial and responsive, even though I was very nasty. But I did. I'm so frustrated at this point. I do get nasty easy, and I don't mean to, my friends. And I love you all. Goodbye.